Now that we have covered everything about our gases, that is from the introduction, all the processes that are required, there is still yet another part to be talked about, which is just a continuation from the previous case that we had, and that is the STP condition from the standard temperature pressure. So we need to understand this about the STP condition. The STP condition, it's a condition that we are having, especially for considering our gas that is talking about the standard, it's called the standard temperature and pressure, the standard temperature and pressure. So my consideration is that it's not about this to say, yeah, okay, they can give you values that are suitable for that. But the major important thing I'm going to talk about that. So these are the standard or the bases, the values, the standard values, pressure and temperature. So at a standard condition, we take our temperature to be at 0 degrees Celsius. And remember that if our temperature is 0 degrees Celsius, it simply means we are at 273 Kelvin. Remember, a temperature in degrees plus 273. That was just going to be 273. And at that condition, pressure is approximated to 101.4 kilopascal, depending with the source that you're using, the textbook that you're using for this pressure. But they can do this. Listen to me. They can have a condition where they give you that it's a standard temperature and pressure, but they give you something different totally from this. You use that information as it is. So my major question or my major part is that what are these and what are we using them for? These values that we have for the temperature and the pressure are the ones that are used at the inlet. So this is when the gas is entering. All right, so these are at the inlet. They work at the inlet conditions. So that means we are talking about T1 and P1. So in major cases, what they do is that they will give you a density which is going hand in hand with the STP conditions. Remember our density measured in kilograms per cubic meter. So yes, you'll be given, let's say you are given a volume or whatever that is happening there. It is for the rest of the question. But at STP conditions, it follows that the density that you are given, maybe it's X kilograms per cubic meter. If it is per cubic meter, it means we are talking about a condition where the mass is X kilograms at that condition. And the volume is taken per cubic meter per each cubic meter. That's 1 cubic meter. So our mass is going to be taken at the mass that is there, the volume, 1 cubic meter. So where are we going to use this? We are going to use this information to calculate, in most cases, they will want you to calculate R. So whenever you want to calculate R, you take at STP condition, you're going to take your PV is equal to MRT. So to calculate R, they will give you already the pressure is there at STP, the temperature is there. You want to calculate R. So the volume and the mass, you don't use according to what you're given on the question. No matter you are given a certain mass to say there's a mass of 1, this or a mass of 3 kilograms and a volume of this at V2 or T1, you don't use those ones. The volume and mass that you use here are the ones that you take from the density. From the density. These ones are from the density. At what? At STP condition. That is the condition there. That is the idea. At the STP condition, the mass and the volume will be given from the density. So you use the density, the formula for density, the units kilograms per cubic meter. We have got the mass kilograms, volume per cubic meter per each. So the volume is 1, the mass is whatever that you be given there. So that's the only part. So like I said, this is only done to calculate this one at STP condition. You only use that, only there. The rest of the questions, you use the exact mass of the gas. You use the exact volume. If it is V1, you use V1. If it is V2, use V2 according to what you're given. Not this one. It only happens at STP condition. So I'm not going to waste much time. The rest is going to remain as it is. So you see that we are given a question here. So sometimes they will give you the conditions. Like I want you to try other questions. If you try question 2 there, we are given at STP, there's a density this, and there we are given, it is compressed from this pressure. Take note, the pressure is different from the one at STP, even the original. You use the one that you're given there. But the idea about calculating the gas constant, you use that part of the density, this one that I explained, the density. You take the mass from there, the volume from there. This one that you are seeing here is the mass that you use of the gas when you are now calculating normal other values, not at STP condition. All right, so we have a question number 1 that I'm going to use as our example because it's the same thing as question number 2. We are given that there is a mass that is of 1,4 kilograms of a gas is compressed, take note, adiabatically. So we are using the law PV to the exponent of gamma. You remember, we talked about the difference between a polytropic PV to the exponent of N and an adiabatic, where we'll see, especially on the heat that is being added or rejected adiabatically, that it is what? It is equal to 0. So that is the major difference that we just have there, but the rest of the formulas are the same. So this is from STP conditions, standard temperature pressure, to 1/10 of its original volume. So the volume, it changed to 1/10 of its original volume. I talked about relating the volumes from V1 and V2. So we've got a mass. In that case, the mass is given as 1,4 kilograms. All right. Then at a condition that we have V1, which is that just the volume. So maybe V1 is just V1. We do not know. But V2, they are saying after being compressed, remember this is being compressed. After being compressed, the volume changed to 1/10 of its original volume. So the original volume is V1. So V2 is 1/10 of that original volume, 1/10 of V1. So that's it. Then we move on here. The density of the gas at STP, the density is this. So you're given 128 cubic meters per meter. So this is the density that you are given, 1.28 kilograms per cubic meter at STP condition. At STP condition, since we are not given, if you check it later on, you'll see that you're not even given the temperature, you are not even given the pressure. They can give, but you're not even given anything. So that is where you take an approximation, all right? So it's going to depend with the value that you use. But for temperature, it is going to be at 0. You take your temperature to be at 0, which is 273 Kelvin, like I explained before. Then the pressure is going to be at 101.4 kilopascal. So this would depend, the 101.4 with your textbook. Some they can give other decimals there after the comma. All right, it's just going to depend with what you're given. But my idea of the question was that at STP conditions, like I explained before, from the density, we are given the mass, 1.28 kilograms. So there is a mass of 1.28 kilograms, which corresponds per each cubic meter of the volume when the volume is at 1 cubic meter. That's at STP conditions from the density. With this information, Nothing else. They will ask you from this to calculate the R for gas at STP condition. That's how you do it. The rest of the calculation, you go back to what you're given, the mass that you have here, the volume that you find. There you are now using exact values. This one, it is ended. But at inlet, because at STP, that is at inlet, it means at inlet, our T, it enters at STP condition, meaning to say it's at 273 Kelvin, and our pressure, it enters at the same at STP, which is 101.4 kilopascal. Yes, these are the values that you are using at STP, but these are also at the inlet, like I mentioned. I think I wrote that one when we introduced. Did I erase those notes, guys? Now I can't see where I wrote my notes, guys. Maybe I erased them. I don't know what just happened. All right, did I just clear those? Okay, no problem. I wrote that to say that is at inlet conditions. All right, we are also given the specific heat capacity at constant volume, CV at constant volume, 0.628 kilojoules per kilogram Kelvin. This is what we have there. So the first question was to calculate, all right, calculate the value of the gas constant, which is R. So you need to calculate R in this case, okay? So how can we calculate R? That is where we go back to the STP conditions. At STP conditions, that is where you determine your R. So that is the only part, only that. Only that part, that is where it plays a role. So remember, from our PV is equal to M RT. So we can calculate R in this case, this one. So you're going to divide by the mass temperature, so that this will cancel. So therefore, our R in this case is would to be PV over MT. That is the pressure at the STP condition, 101.4 times V, the volume there, which is 1 from the density. Then the mass from the density, it was 1.28 times T, which is 273. That's at STP condition. We can have the value of R. Just like that. Just like that. So this was going to give us 0.29017, something like that. So it's going to be 0.29. All right. That's kilojoules per kilogram Kelvin. That's it. So we have R there. We now have R. With this R, guys, I want you to understand this. We are going to use in our simplification to answer any question. This is the gas constant. Whether we use the STP condition, but it is the same that we have throughout. So that is the condition of STP. We're done. We're done with the STP. The rest, we go back to our usual calculation. All right, so even this density thing is no longer there, this one. I'm just gonna not talk about this for now. All right, so now we are back to these condition. Condition what? Condition 1 to 2. All right, remember, it's being compressed. So as we know that we are going up 1 and 2, we've got a V1, V2, the pressure is increasing from P1 to P2. While the volume is decreasing, the pressure is increasing. I talked about that on our introduction. Compressed, it is going to affect our work done. Work done under a compression, it's a negative value. All right, so we have got our R there. Let's move on to B, the value of CP. So where do we obtain the value of CP? So remember, we talked about the relationship that occurs between R and RCV and CP. So we can actually use that. Remember, R is equal to the difference CP minus CV. We have CV, we have R, so you can make CP the subject. If we transpose CV, or just substitute R is 0.29 is equal to CP, the one that we want, minus CV, 0.628. So if I transpose this to the other side, it becomes a positive. That's 0.29. 0.29 plus 0.628 is equal to CP. So this is the specific heat capacity at constant volume, at constant pressure, P. at constant pressure, which is 0.918 in kilojoules per kilogram Kelvin. All right, we've got our CP there. So we do not know. Maybe we might need this. Let us just write it aside. We calculated also our CP 0.918 kilojoules per kilogram Kelvin. That's it. All right, so just like that. So you see, guys, this is now interesting. We talked about all these formulas. Just need your formulas there. All right, then the other part, the value of gamma. All right, we are just given that is adiabatic. True, we are not given gamma there. So how are we going to calculate our gamma? We had a similar question like this, if you still remember, on the introduction, but it was to calculate N. We had a question like this, but this one we are supposed to calculate gamma. But we had this question. All right. So we can, because, okay, we do not have that one, it was because we had pressure and so forth. So this one, we are limited. We do not have those pressure, P1 and P2. Remember, when I talked about this one, P1, V1 to the exponent of gamma is equal to P2, V2 to the exponent of gamma. If we're given P2, we're going to calculate it because we can just use our formula to make gamma the subject, but we do not have. So thank God we have the constant CP and CV. So we can calculate our gamma from there. Remember, gamma is what? The ratio between CP and CV. That means we're going to just divide our CP. We calculated 0.918 kilojoules per. This is the same units also, so that's a constant. CV, which is 0.628. So that was going to give us gamma in that case. And our gamma was going to be 1,46462, something like that, and so on and so on. So that is it. So this one was straightforward. All right. I was actually mistaken it to another question that we did where we can play with that formula, but we are going to need that formula. Definitely, that one, we can't leave it. The original and the final volumes. So there we are supposed to determine the original volume and the final volume, that is V1 and V2. So take note, those, the density that we talked about, those volumes that we talked about, that this is mass, no, they're out. They are no longer. They just worked at STP to calculate R. So to calculate the volume V1 and V2, we are back to the simplification that we are used to. Which is it that we are used to? As long we can relate to here, like I said, we do not even have P2 or T2 here, so it's going to be complicated. So we can use the PV. PV is equal to MRT, but it follows that if we take T1, P1, that means we can be able to find V1. All right, so let us make V1 the subject. Just going to divide by P1. So volume is going to be MRT1 over P1. So that is V1 as the mass. We are back to the original consideration of our gas. Our gas is at which mass? At 1.4 kilogram. That is the mass of the gas, 1.4. So we are back to that. So we have got 1,4 there times R, which is 0.29 times T1. We have already our T1, which is 273. Remember, I said at STP, those are also values at inlet. Those are values that occurs at inlet. So for pressure and volume, you take those values at what? At STP as your pressure and what? Temperature. So remember, we said pressure is 101.4 kilopascal. So that was going to give us V1, which is 1,093 cubic meters. We have V1. So with the V1, the other question was to calculate now V2. All right, now we need V2. So remember, V1 was 1.093 cubic meters. So how are we going to have V2? So if we are to use the same formula, is it going to work? We have to check first. Because remember, formula, we are supposed to have everything. So if we use the PV, it's not going to work because we do not have, at these conditions here, we do not have anything. Oh, guys, this is a ratio. Why do we think of the formula? There is a ratio there. Let us just use the ratio. V2 is 1/10 of V1, an advantage that is straightforward there. V2 is 1 over 10 of V1. We are already given that. So that's 1 over 10 times V1, 1,093. Since it is a compression, we are going to have a lesser volume. Remember, the volume decreases under compression. So that was going to give us 0,1093, which is 0.923 decimal places in what? Cubic meters. So that's it. Just like that. So we have V2. That's V2, the volume is equal to 0.109 cubic meters. We just got it from this relationship that we talked about before. All right, just like that. Just like that, we can attempt any question using those formulas that we had from our introduction. All right, let's move on to another question. It was to calculate the final pressure, P2. Where and how can we calculate P2? We do not have T2 here, so we can't use PV is equal to MRT because we need temperature there. But remember that between this volume, because we've got V1, we have V2, we have P1, we can calculate P2. From which formula? Remember, from our PV formula. But I said that this one is no longer P1, V1 is equal to P2, V2. No, because of the adiabatic process, there is gamma there. We raise volume to the exponent of gamma. For a polytropic, you're going to use N. So there we can calculate P2. Is that so? Yes, we can just divide there because this one is not that complicated. Just divide by V2 to the exponent of gamma like this. We are done. So whether you want to make certain arrangements there, it's up to you. But this is just direct. I can just substitute because I have P1. There's no need for me to just work out there. 101 for P1 at the inlet. Remember, that was 101,4 times V1 to the exponent of gamma, which is this one. And that would be 1,093 to the exponent. Remember, our gamma was, we calculated it was 1,462. We calculated this, everything over V2. We also calculated V2. Remember, we got 0,109 to the exponent of gamma, which is 1,462. So just like that. So yes, we can combine whatever that you do there. It's up to you. The question is that as long we have manipulated and see the formula for P2, we can determine the value of P2. So that was going to give us, remember, the pressure is increasing under a compression. So that was going to be 2,949,735 in kilopascal. Just like that. So we have P2 there. All right, just for the sake, we do not know, maybe we might need this value. Remember, I say 2,949,735 kilopascal. So that is our T2. All right, that is our P2, I mean, the pressure, talking about P2 there. So you need to understand this. Then the change in internal energy, under an adiabatic process. How do we calculate the change in internal energy? Remember that we said under an adiabatic process, the change in internal energy is CV into the change in temperature T2 minus T1. We talked about this formula. All right, guys, I want you to watch the video on the introduction so that you be together. So this is our formula. We need the mass. The mass is already there. CV, we already given. T2, we do not have. T1, we are already given at STP condition. So where are we going to determine the value of T2? Remember, we calculated the pressure. We have V2, we have R. So we can use the PV formula. PV is equal to MRT. So from that, remember, PV is equal to MRT. This is 2, 2, this is going to be 2. So we need T2 there. You can just divide by MR. So T2 is equal to P2 V2 over mR. So that's T2 is P2, V2. P2, what are we having? 2000. So this is P2, 2949.735 times V2. If we are to check V2, it was 0.109. Everything over the mass. That's the mass in this case is 1.4. So the mass there is 1.4 times R, which is R we calculate. That was the first thing that we calculated, 0.29. So that was 0.29. Remember, it was the first thing that we calculated. So this was going to give you the value of T2. All right, I'm realizing that as for me, guys, I actually used another formula there. I used this one, no problem. I'm going to also explain it. Remember, we have got this formula that relates T2 and T1. T2 over T1 is equal to V1 over V2 to the exponent of n minus 1. So it's going to be gamma minus 1. We had that under a polytropic, which also the one that we equate to the pressure is supposed to be equal to, remember, it's P2 over P1 to the exponent of gamma minus 1 over gamma, like that. So you can calculate T2 from there. If we do cross multiply here, that means T2 is going to be given as T1 into V1 over V2 to the exponent of gamma minus 1. Thus, T2 is equal to T1. Remember, T1 we had before at STP condition, it was 273. So that's 273 into V1 over V2. So the V1 over V2, that's where you go back to the ratio that you are given there. Remember, or you can just substitute because you have V1, you have V2, or you can just use the ratio. The V1 over V2 is going to be V1 over V2. Remember, the V2 was given as 1 over 10 of V1. So it's going to be 1 over 10 of V1. So this will cancel. 1 divided by 1 over 10, it's a 10. So this gives us a 10. So this is 10 to the exponent of gamma, which is 1.462 minus 1. So you can actually use this. And that was going to give us T2, which is, in this case, this is the one that I used. But that one, you can also have the same thing. 790.975 Kelvin. All right, so that is our T2 that I'm going to use to calculate the change in the change in internal energy, because there we are at least using original values. That's the major reason I chose this. This is an original value that we never changed anything. This is originally from the ratio. It's only this value that we calculate. But here we calculated P2, we calculated V2, we calculated even the R. So the answer is not going to be exactly that answer that is the one that you want. But if you use that, use the one that you want to or use there, still one and the same. So this was going to be like this: 2,949,735 times 0.109, everything over 1.4 times 0.29. So that was going to be, you see, this one will be 791, this. So if you are using this, use as it is, all right? So you can even change this to 3 decimal places. Let's fix this to 3 decimal places. All right, so that's 791.924. 791.924 Kelvin. So this is what we are having there. So if you are using this, it's fine. You work with that one. But like I said, guys, for my preparation, I already worked with this one, the first one. So I'm going to take this T2. All right. So using that T2 that I calculated in the first place, this one of 790, I'm just going to substitute here. I have the change in internal energy, the mass at 1.4 kilogram times the specific heat capacity at constant volume, 0.628 times the change in temperature T2, the one that we just calculated, 790.975. So I'm going to use this one. So if you're using the other one, it's up to you guys. Use whatever that you want. minus T1, which is the temperature at the inlet, 273, remember, at our STP condition. So that was going to give us the change in internal energy, which was going to be 455. This is 455,404 kilojoules, just like that. Just like that. So this is your STP condition. Your STP condition is just a normal calculation throughout. The only part that you need in the first place is when you are dealing at STP condition from the given what? From the given density. From the given density that you are given. It is the one that you use to find the volume from there and the mass. It was mass and volume there that we had. With the temperature and the pressure at STP, volume, mass, temperature, pressure is enough for us to calculate R. So they won't give you R because they know that you'll be having full information necessary for you to calculate for R. That's it. Just like that. So these are the typical questions. Let us try to do as many questions as we can so that we revise, preparing ourselves for the exams that are ahead of time. But for now, that's it, guys. Till we meet again.